Hey guys, good morning. This is Mrs. Drajewski. Today we are going to be talking about some convergence tests. This is going to be the first in a series of videos we're going to do about this. So today the convergence tests we're going to focus on are the nth term test, the comparison test, and the limit comparison test. I think you're going to like this. So if you recall from year one, we talked about finite and infinite geometric series. And a geometric series is basically one that has a common ratio that gets multiplied through each time to generate the next term in the sequence. And when we have a finite one, we're looking at a specific certain number of terms in that sequence. And with an infinite series, it's one that never ends. There's not a specific number of terms. If you're asked to find the sum of a particular term or number of terms in an infinite series, you're finding what's actually called the partial sum of that infinite series. So today we're going to be talking about some limits that involve these sums. They're all going to involve the Greek letter sigma. So here's like our first definition. We're told that if the limit as n goes to infinity of s sub n, this is our series, is equal to the sigma exists and equals some finite value of s, then the infinite series is convergent. Otherwise, it's divergent. Now, this is just a definition, and what it basically says is that if the sum to infinity is possible to calculate, then the series converges. And we actually already knew that from year one. But for many of the series we're going to look at, it's not going to be that easy to find the sum to infinity. So we're going to need to test for, we're going to need to use some other tests to test for convergence. If you can calculate that the series converges, then go ahead. If you know what the sum to infinity is, then use that, and that shows that it's convergent. But sometimes we can't just tell what that common ratio is. We can't just make that assumption. Also, if the series is convergent, then the limit as n approaches infinity of that series is equal to 0. Now, the converse of this is not true, and it's easy to get it mixed up, so you got to be careful. If the limit is equal to 0, it does not mean that the series converges. So it just means that a convergent series has this limit as n approaches infinity of 0. Just getting that the limit is 0 does not tell you that it's convergent. So please do not assume that that's the case. It doesn't go backwards. So this leads me to the next step in our notes, which is how do we tell if this series diverges or not? Because it might actually be easier to show that a series diverges than it is to show that it converges. So if the limit does not exist, or if the limit does not equal 0, then the series has to be divergent. That is totally true. So it's much easier to see like, hey, I just calculated the limit. I didn't get 0. And I calculated the limit and the limit didn't exist. That tells you that the series has to diverge. So that's pretty awesome. It might be easier to show that it's divergent than convergent. So the converse of this is true. If the limit does not equal 0, you can totally assume that the series is divergent. Isn't that pretty awesome? I think so. So this brings us to example number 1. We're supposed to show that this series diverges. Excellent. So kind of like my plan here is to show that the limit doesn't equal 0 or that the limit does not exist. If I can show that the limit isn't 0 or that the limit doesn't exist, then I've shown that it diverges. So how do I do that? Well, this is actually kind of fun. We've done it a little bit before. I'm going to try and simplify this up so that I don't have a term with an n in the numerator. So let's let a sub n be equal to this whole guy right here, n squared plus 3n plus 1, all divided by 4n squared plus 3. Okay, so I'm going to take the limit of this bad boy, but I'm going to divide every single term by my highest exponent or power of n so that I can take the limit of each individual term. So let's take the limit as n goes to infinity of, I'm going to divide everything by n squared. It's my highest power of n. So n squared divided by n squared plus 3n divided by n squared plus 1 divided by n squared. That's my whole numerator. Fantastic. Now let's go for the denominator. I've got 4n squared divided by n squared plus 3 divided by n squared. Now I'm going to go ahead and reduce, simplify this out. When I do that, n squared divided by n squared is 1. Well, let's actually write it out as the limit as n approaches infinity. Oh, good gravy, I lost it over here. So then we've got 1 plus, let's see, 1n cancels out one of the n's down here, so that's going to give me 3 divided by n. And nothing's going to reduce here, so I've got 1 over n squared, and that's great. Now down below, my n squared's reduced to 1, so I'm left with 4. And there's nothing for, there's no n's on top here, so nothing's going to cancel out. And I've got 3 divided by n squared here. Now I'm ready to take the limit. So as n gets super duper big, 1's going to be 1 because there's no n there to affect it. Here, 3 divided by n, well, if n gets really big, this is going to shrink and shrink and shrink until it's almost nothing. So we'll say that approaches 0. And the same thing here. It's just going to go to 0 faster. Down below, there's no n to affect 4. That will stay 4. And 3 divided by n squared, as n gets super big, is also going to shoot to 0. So it ends up getting a limit that's 1/4. Now, all convergent series will have a limit of 0. So does this converge? Absolutely not. When the limit does not equal 0, the series diverges. So let's write that as our final statement. Since the limit as n approaches infinity of a sub n does not equal 0, the series diverges. And we're done. That is all we needed to do. So no need to show that it converges. In fact, we couldn't because this one diverged. It's a lot easier just to show that the limit doesn't equal 0. Hope you guys liked that. Since we cannot assume from the nth term test that a series is convergent, we're going to need more tests. So they're not always going to be that straightforward. And sometimes we're not going to be asked to prove that something diverges. We're going to be asked to prove that something converges. And again, finding that the limit equals 0 is not enough. Every convergence series will have a limit that goes to 0, but not every series that goes to 0 will converge. So it doesn't go backwards. So we've got some other tests to help us with this. And I've shown you where they're at inside of our textbook. I'm going to have videos for each one. I'm going to continue along today. In this video, we're going to go ahead and talk about the comparison test and the limit comparison test. So here we go, the comparison test. Now we actually already talked about this previously, and I'll try and put a link in the video so that you can go back and check that video out. So we did this for improper integrals as well. So what we knew was if we had a positive sequence, we'll call it a sub n, and another sequence, b sub n, that was always larger, then if b sub n converges, then a sub n, the smaller one, would also converge. Conversely, if a sub n was the larger sequence and b sub n was the smaller one, then if b sub n, if the smaller one diverged, then so did the larger one. So basically what this means is you got two series of positive terms. The terms of the second one are always bigger than the terms of the first series. Then the second series is convergent, and so is the first. And it goes backwards. The hardest part of this, as before, is picking that appropriate second series to compare with. Usually I like to find clues in the original problem that we're given, and usually I try and graph it to see if it's the bigger function or the smaller one. So here we are, example number 2. So we are asked to, I'm going to hide this for a second. Whoa, that was pretty big. We're asked to test this for convergence. Now, the nth term isn't going to work for us because that just is going to help me find if it diverges, and that's not really going to be enough here. So what I want to do is try and use the comparison test here. Unfortunately, I don't know what we could compare it to, right? So the first step that I took was to go ahead and graph it. So here it is on my calculator. You know what? Let's go ahead. This should be +3. There we go. Let's go ahead and graph it. See what happens. Ooh. All right, so it looks like it's above the x-axis, and then it starts to decrease and it goes down below. We can zoom in a little bit, but what I really want to do is compare this to a function that is always going to be above or that's always going to be below. So what could we compare it to? Well, the clue is in the function, right? So I'm looking at 1 divided by 2 to the x power plus 3. What if we try 1 divided by 2 to the x? Let's look at what happens there. Whoa. This looks like it's a larger function. Looks like it's always above, right? So we can zoom in. Let's see, Z-box, my favorite zoom. And since we're looking at it from 1 to infinity, let's Z-box in on values that are relevant to us. Let's see what's happening in this area here. Okay. So a little concerned. It is okay if they equal each other. So I guess I'm not really that concerned. It does appear like it's always above. I don't see the blue graph going above. That's our original function. 1 divided by 2 to the x is this red function. So let's check it out. Let's compare them and see what happens. All right. So let's let b sub n equal 1 divided by 2 to the nth power. Okay, and if that's the case, they're all positive, so 0 is less than 1 divided by 2 to the n plus 3, and that is less than 1 divided by 2 to the n. And it could also be equal to, well, this is not going to equal 0, but these could be equal. So I guess I'll put my equal sign in here. But remember, we want to compare it to something that we can actually find the limit of, because if we can show that this one converges, then we can prove that this one converges. Or if we can prove that this one diverges, then this one diverges as well. So let's see, what is the limit as n approaches infinity of this new one we just came up with, and we're going to compare with, which is of course why we call it the comparison test. What is the limit as n approaches infinity of 1 divided by 2 to the n? Well, as n gets really, really big, this denominator is going to get really big as well. This is going to go to 0. Is that enough to tell us that it converges? Absolutely not. It might. Every convergent series is going to have a limit as n approaches infinity of 0. However, that certainly doesn't mean that it converges. Remember, all convergent series have a limit that goes to 0, but just having a limit that goes to 0 does not mean it converges. So, does it converge? Maybe. It's possible. Now, if I would have had a limit that wasn't equal to 0, I would know right away that it didn't. But how can we test for convergence? Well, let's calculate the sum to infinity. Of course, in a geometric series, the only way we can do that is if our common ratio is its absolute value is less than 1. So let's look at how this is written now. I can unhide this giant box here. Whoa, hey. There we go. So remember from exponent laws that 1 divided by 2 to the n is equal to 1 to the n divided by 2 to the n, which is the same as 1/2 to the n power. I actually think it's easier to see this backwards. If we've got 1/2, to the n power, then we can raise the numerator to the nth power and the denominator to the nth power. 1 to whatever power is 1, no matter what. So we can actually rewrite this guy as being the sum to infinity of 1/2 to the n power. And this is a geometric series whose R value, in this case, is 1/2. And 1/2 and its absolute value is less than 1. So therefore, I can tell that in this geometric series that the sum of 1/2 to the n power converges, since that common ratio is less than 1 and positive. Now from the comparison test, if our larger series converges, then the smaller one converges as well. So by the comparison test, our original function or original series converges. And there it is, the comparison test. So now let's move forward and let's try the limit comparison test. So for the limit comparison test, here's our official definition. But what does it mean? I'll give you a second to read that over. Yeah, it's pretty dense. So basically, if we calculate the limit as n goes to infinity of our first sequence divided by the second sequence, that value is going to tell us about the convergence of the two series. So if the result, if that limit gives you a constant, just the number, then what that means is that both sequences are going to converge or both sequences are going to diverge. Now, if the limit goes to 0, then both of those sequences will converge. If this limit goes to infinity, then both sequences are going to diverge, or if the limit doesn't exist. Okay, so let's check this out. Okay, so let's see. Let's determine if this is convergent or divergent. Now, you are only given one series here, right? So when you are going to use the limit comparison test, pick a series that you already know the convergence about. And I think it's a good idea to pick one that does converge. So looking at this problem, What series do we know that converges? Well, I think we can use the same one we used on the last problem. Let's let b sub n be 1 divided by 2 to the n. Do you see how I'm still using that the function to help guide me into a good choice? I think that that's a good idea. So let's let b sub n equal 1 divided by 2 to the nth power, which we also know is equal to 1/2 to the nth power, right, from our exponent rules, which converges. Okay, so let's divide them. Let's see, we've got the limit as n approaches infinity of a sub n, the one we were given, so 1 divided by 2 to the n minus 1, all divided by b sub n, our new one, which is 1 divided by 2 to the n. You could use this one too, but I like this nicer. So this has created for us a complex fraction. Ooh, so that's okay. A complex fraction is easy for us to simplify, and that's what I'm going to do next so that it doesn't look so complex. I'm going to multiply by the reciprocal. So I've got 1 times 2 to the n, which is 2 to the n, and 2 to the n minus 1 times 1, which is 2 to the n minus 1. So I'm just multiplying by the reciprocal. Oop, I forgot my limit. They're sneaky. You know what? Let's see if I can just move it over. I cannot. All right, well, you guys know that I have the limit there. Okay, so now what I'm going to do is I'm going to simplify. I'm going to take the limit. Now I'll write it as n approaches infinity. I'm going to simplify it, and I'm going to have a dividing by 2 to the n power party. Yep, it's just the kind of party I would like to go to. So I'm going to divide every single term by 2 to the n. 2 to the n divided by 2 to the n, 2 to the n divided by 2 to the n, and 1 divided by 2 to the n. What this is going to do is going to make it a lot easier for me to calculate the limit. All right, so let's simplify this bad boy. I've got the limit as n approaches infinity of 1 divided by 1 minus 1 divided by 2 to the n. I think we're ready to take the limit now. If we take the limit, as n approaches infinity, 1 is still going to stay 1. 1 is still going to stay 1. But as n gets really, really, really big, this denominator is going to get huge. And 1 divided by something that's getting larger and larger is going to go to 0. So here I get that the limit is equal to 1. Remember, you have to follow the rules for the specific test that you're trying to take. With the limit comparison test, if you take the limit and you get a constant number like we just got, then both sequences are going to converge or both sequences are going to diverge. So let's not be so huge. Here we go. Since 1 is a constant, both series converge or diverge. And since we know that b sub n converges, a sub n has to converge as well. Therefore, the sum from 1 to infinity of 1 divided by 2 to the n minus 1 converges by the limit comparison test. And we're done. I think this one was great. I enjoyed that. I hope you did too. All right, so let's have you guys try this one. So go ahead and pause it and see if you can follow along with example number 3 and use that to help guide you through problem number 4. So go ahead and pause it now, and then I'm going to go ahead and work through it, okay? Like I said, the first thing that's probably the toughest part of the whole problem is actually picking the sequence that you're going to compare it with. So I would choose one that you already know converges. I would use a geometric sequence like 1 divided by 3 to the n per se, because that one does have a common ratio of 1/3, and that meets the requirements to show convergence of a geometric sequence. It just has to be between 0 and 1. So I'll just take the limit as n goes to infinity of 1 divided by 3 to the n minus n, all divided by this series that I know converges, 1 divided by 3 to the n. I can simplify that out, and this time I'll remember my limit sign. Oh, goodness me. And since this is a complex fraction, I can multiply by the reciprocal. So I'll get 3 to the n divided by 3 to the n minus n. Easy to simplify. All I have to do is just divide every single term by 3 to the n. Let's go. Everything is getting divided by a 3 to the n party. So it ends up being just like you're dividing it by 1 or you're multiplying by 1. And when we simplify that out, I get the limit as n approaches infinity of 1 divided by 1 minus n divided by 3 to the n. Now I'm going to take the limit here, and when I take the limit, as n approaches infinity, 1 is going to stay 1. That's nice. 1's going to stay 1. Okay. And then we have to just think about the effect of n getting really large, right? So as n gets really large, my numerator is going to get pretty large. But my denominator is going to get even larger. So this limit is going to be 0, since my denominator is growing faster than my numerator. So this is going to give me 1. Again, this is a constant. Okay, so I was just looking for a constant, and the limit comparison test says, hey, if you get a constant, it doesn't say that it converges. It says it either converges or it diverges. Both of them, sequence A sub n and B sub n. But since we already know that B sub n is a convergence series, then we know that A sub n has to be as well. So therefore, the sum from 1 to infinity of 1 divided by 3 to the n minus n converges by the limit comparison test. And that's it, we're done. And that's what I have for you in this video today. And I'm going to post up the next video, which is going to be me talking about the integral test and p-series. So good luck. I hope that made sense. And let me know if you have any questions. Bye-bye.